In this video, we will analyze a more complex situation involving free fall motion. But before we do so, let's watch a video. What you saw in the video was a ball thrown upward with a positive vertical velocity that came back down and hit ground level. And because ground level is lower than the height at which he released the ball, the overall displacement from when he threw it to when it strikes the ground will not be zero. Here are some other keys to understanding this motion. First of all, the ball is in free fall motion as soon as it leaves his hand. What that means is we can use A equal to negative G, which is equal to negative 9.8 meters per second squared, at all times when analyzing this free fall motion. The ball that he threw had a positive initial velocity because he threw it upward. The ball travels upward and reaches some maximum height above its release point, and then it starts coming back down towards the earth. And remember, at the maximum height, the ball's velocity is zero because the ball is changing directions. I paused the video very close to the maximum height. Remember that the ball's velocity at this point in the trajectory is zero. Our next key is that the ball will strike the ground with a negative velocity. If we watch the ball come back down towards Earth, we will define the velocity as negative from here on out in the video because we typically take downward to be the negative direction. And finally, the object will hit the ground at a height that's lower than the height that it was initially thrown from. What that means is that the overall displacement in this situation will be negative. We will now consider a similar situation and do some problem solving. Here you see someone standing near the edge of a cliff and throwing a rock straight upwards. On its way down, the rock will just miss the edge of the cliff and will fall all the way to the bottom of the cliff and hit the ground 7 seconds after it was thrown. In a moment, please pause the video, consider the 5 questions you see here, get out a notebook or some loose leaf paper, and try to solve these problems. Once you finish, go ahead and play the video, and you'll see how I worked out all the solutions to this problem set. Okay, welcome back. Let's now go through the answers to the 5 problems that were listed. The first problem asks, how long after being released does the rock reach its maximum height? Let's start off by making a list of what we know. The initial velocity of the rock is 24 meters per second. At the maximum height, the rock's velocity is zero. Remember, at the maximum height, the rock will change directions and start moving in the downward direction with negative velocity. It's important to remember that I'm only considering the motion of the rock from when it was thrown to when it reaches its max height. That's why the initial velocity I've defined to be 24 meters per second, and the final velocity I've defined to be 0 meters per second. In order to solve this problem, I only need to analyze that portion of the rock's trajectory. Now, we're trying to solve for time, meaning that time is the unknown. And one final important piece of information is that the acceleration in this situation is the acceleration due to gravity, which is negative 9.8 meters per second squared. If you take a moment to go through your kinematics equations, you'll probably see an equation that has these 4 variables in it, and here is the equation that fits that bill. By the way, this is the exact same equation I'll use in number 5 to create my velocity versus time graph for the motion of this rock. But for now, I'm going to solve this equation for t. First thing I'll do is I'll subtract the initial velocity to the left-hand side. Now I'll divide both sides by a, and what I now have is an expression for time that says time is equal to the final velocity minus the initial velocity divided by the acceleration. I will now plug in the information that I know, and if I simplify this, I get negative 24 meters per second divided by negative 9.8 meters per second squared. A negative divided by a negative will give a positive. You should always get positive values for time. In fact, if you ever get an answer of negative time, you should probably go back and check your work because odds are you did something wrong. The unit will come out to be just seconds, and my final answer to 2 significant figures is 2.4 seconds. What this means is that 2.4 seconds after the rock was released, it will reach its maximum height. The second question asks, what is the maximum height of the rock relative to the height that it was thrown from? You need to use your answer to question 1 because you just solved the time it takes for the rock to go from the height it was thrown up to its maximum height. So I'm going to write that number down right away. The initial velocity for this situation is still 24 meters per second. At the maximum height, the velocity is 0, and as is always the case for freely falling objects near Earth's surface, the acceleration in this situation is the acceleration due to gravity, which is negative 9.8 meters per second squared. Because we're trying to solve for the maximum height, I need to realize that we're trying to solve for delta x, that is displacement. As you can see, I just defined the initial position of the rock to be 0, and now I'll use the kinematics equation that has delta x, a final velocity, initial velocity, and time in it. if you take a look at your list, there is an equation that has all of this information in it. But some of you may have realized that there's another equation that we could possibly use to solve for the maximum height in this situation. In fact, either one of these equations will get you the right answer for delta x. The left-hand equation has a time variable in it, meaning that you'd have to use your answer from question 1 in that equation. But the right-hand equation, the square of the final velocity equals the square of the initial velocity plus 2a delta x, has no time variable in it, meaning that you could have solved this problem without having to worry about the time it took for the rock to get to its maximum height. Either way, here's what the two equations will look like when you plug in all the information from this problem. I didn't include units because I was a little crunched on space, but you can go ahead and solve either of these. Know that your final unit will be meters, as it usually is for delta x, and regardless of what equation you chose in this situation, your final answer should be delta x equals 29 meters. To solve problem 3, we want to determine the height of the cliff. To begin this problem, I'm going to label some information that I already know. In the previous problem, we determined the maximum height of the rock to be 29.4 meters. It also tells me that the person released the rock 2 meters above ground level atop the cliff. So the height of the cliff can be defined to be the height from ground level down to where the rock hits the ground 7 seconds after it was thrown upwards. I'm going to use this equation because the problem tells me the rock hits the ground 7 seconds after it was thrown, meaning that time equals 7 seconds. The initial velocity in this problem is 24 meters per second. The acceleration is negative 9.8 meters per second squared. And with those three pieces of information, I have everything I need to solve for delta x. Here's what the equation should look like with all the numerical values in place of the variables. So go ahead and get out a calculator and crunch down these numbers, and you should get a final answer of delta x equals negative 72 meters. But be careful, this really isn't the final answer because that's not the height of the cliff. That is the rock's displacement from the height that it was initially thrown from. In other words, the answer you have is this distance right here. We want to solve for the height of the cliff, not for the rock's displacement from the height that it was thrown from. But remember, the rock was thrown from a height of 2 meters above ground level at the top of the cliff. So if we simply take out that 2 meters from the delta x equals negative 72 meters, the height of the cliff is really just 70 meters. Problem 4 asks you to solve for the velocity of the ball just before striking the ground. We know the ball strikes the ground at time equals 7 seconds. The initial velocity for this situation is 24 meters per second, as it has been in all of these problems. We don't know the final velocity, so I'm going to put v sub f equals question mark. And as is always the case when we have freely falling objects near a surface, the acceleration in this situation is negative 9.8 meters per second squared. If you take a look at your list of kinematics equations, there's a very simple equation that has this information in it. Here is that equation, that nice simple linear function. And because we're trying to solve for final velocity, all you really have to do is plug in the numbers. And you should get a final answer of v sub f equals negative 45 meters per second. Don't lose that number, because for question 5, we can actually use that in creating our velocity versus time graph. We now know that the velocity at time 7 seconds is equal to negative 45 meters per second, and that will be an ordered pair on your velocity versus time graph. Okay, for question 5, here are the two graphs that you should have produced. I did these in Microsoft Excel. You notice that my velocity versus time graph is linear. The initial velocity in this situation is positive 24 meters per second, as you see up here. This rock's velocity decreases uniformly by 9.8 meters per second every second of its motion. You can actually see that in my table of values over here to the left. Notice that the velocity of the rock is 0 right around the t equals 2.4 mark right here, meaning that at 2.4 seconds, the velocity of the rock was 0. It changed directions and started falling back down towards Earth's surface. And then from 2.4 seconds on, notice that the velocity of the rock is negative, and its velocity is now increasing in the negative direction as it falls towards the ground below the cliff. As we already calculated, the velocity of the rock just before it strikes the ground at time t equals 7 seconds was about negative 45 meters per second. The other graph you were asked to create was a position versus time graph. This is a pretty interesting looking graph. We can see that the rock reached its maximum displacement at about time t equals 2.4 seconds. And remember that the slope of the line tangent to the curve at 2.4 seconds should be 0. and that corresponds to the velocity of 0 in my velocity versus time graph. And I've already stressed this in previous videos, but the slope of tangent lines to this position versus time curve will directly correspond to the values you see in your velocity versus time curve. As an example, let's look at t equals 4 seconds. I'm going to fit a tangent line to my position versus time curve at t equals 4 seconds, and the slope of that line you see right there should be about negative 15.2. I know that because if you look at the velocity versus time graph, at t equals 4 seconds, notice that the velocity is negative 15.2 seconds, and the slope of the line tangent to the curve on a position versus time graph gives you the instantaneous velocity of the object. If I draw a tangent line to the curve at t equals 2 seconds, notice that this line has a positive slope, but it's somewhat flat, meaning that I wouldn't expect the magnitude of the instantaneous velocity to be a very big number. Well, sure enough, if you look up at the velocity versus time graph at t equals 2 seconds, the magnitude of the velocity is not very high. It's about 4.4 meters per second. Feel free to go ahead and pause the video, look at these two graphs in detail. Hopefully you're able to produce these two graphs. And more importantly, I hope you understand the information contained in the graphs that you see on the screen. Okay, thanks for watching. In the next video, we'll consider a rocket launch example. And as we wind down our study of kinematics, feel free to go back, rewatch old videos, or ask any questions that you may have.